Graphic display reproduction is now used in a plethora of applications. Over the years, the graphic architectures employed have changed considerably. The 60s saw architectures based on specific display list instructions that drew lines and objects using specific processor units and were very resource heavy. In the 70s, scan-convert architectures translated incoming data streams into bitmap video, laying the foundation for 3D. Atari's 2600 circa 1977 was based on this. Frame buffer architectures had emerged by the 1980s. One example was ATI's color emulation card used in Commodore computers during this era. In the 90s, an explosion of algorithmic graphics processing occurred. Graphic accelerator cards arrived, including Silicon Graphics OpenGL and Microsoft's DirectX. The introduction of 3D add-in cards in 1995 finally enabled migration from more prosaic 2D graphics. The new millennia saw complex graphics processing enter the mobile market, with Nokia's N-Gage and Sony's PlayStation Portable. Via OpenGL and DirectX, programmable graphics processing was added. Let's consider a typical graphics controller solution. The host interface is typically a parallel bus, providing the throughput capacity for sustaining high graphics data. As there's data sharing, the memory controller provides memory management, whether the physical memory is on or off chip. The GPU core processes graphics data. Traditionally, a large frame buffer memory holds complete frames of bitmapped images for display via the display controller. Next, let's look at a particular case. A household appliance user interface requiring sound, touch and display functions, plus low implementation cost. The solution proposed here offers a complete parallel engine for graphics, touch and audio on a single chip. The serial bus acts as the host interface, reducing pin count and packaging costs. A serial bus interface also means that data transfer between the microcontroller and the graphics chip is relatively low, so a lower performance microcontroller can be specified. DisplayList memory stores primitive objects, replacing a large graphics memory. Higher level graphic widgets can also be implemented as display lists, including clocks, keys, gauges, etc. To ensure seamless transition between the microcontroller updating the display list and display controller refreshing the panel, a ping-pong mechanism completes updates on screen through register commands. The graphics engine executes lines, points, rectangles and graphs, as well as alpha blending, shadowing and anti-aliasing operations without microcontroller involvement and allowing significant reductions in memory requirements. It executes a display list once for every horizontal line, processing the primitive objects in the list and constructing the display line buffer. The horizontal pixel content in the line buffer is updated if the object is visible at the horizontal line. Hence, this architecture dispenses with large frame buffers. Instead of traditional touch scanning and XY coordinate response, invisible tags are assigned to buttons or keys. For touch events within a tag area, an associated tag number is fed to the microcontroller, saving processing resources. FTDI's embedded video engine, with its object-orientated approach, facilitates implementation of more sophisticated embedded displays while keeping within budgetary constraints.